Hi guys, today we'll be discussing about rocket propulsion. As we can see, a rocket is being propelled to this direction and the gas is being ejected in the opposite direction. This is due to Newton's third law, the action and the reaction. Here when we apply law of conservation of linear momentum, we can see the exhaust gas, the fuel and the mass of the rocket are the things to be considered. We will also be finding the thrust and the velocity change associated with it. Let us consider two situations of the rocket. Initially, the rocket carries a mass m, which is the mass of the fuel as well as the mass of the rocket. And at this moment, the rocket is traveling with a velocity of v. And also in the other situation, after a particular time of t plus delta t after the initial motion, the rocket is said to be moving with a velocity v plus delta v, and at this particular instant we can see the mass is being decreased, so the mass would be m minus delta m. As the fuel is being combusted, the total mass of the rocket would be decreased, so we get this m minus delta m term. This particular moment, the rocket is ejecting the gases which are burned due to the fuel. So we get this velocity as v exhaust velocity, and this v exhaust is the velocity of the fuel combusted relative to the rocket. Here we consider a situation where there are no external forces acting on the rocket. So we can see by the law of conservation of linear momentum that the initial momentum is equal to the final momentum. Now let us simplify it with the equations. So we know that the initial momentum is m times v. This would be equal to m minus delta m times the increase in velocity v plus delta v plus the reduce in the mass delta m times v minus v exhaust. Now you must be wondering why this term is v minus v exhaust. Here we know that the velocity of the fuel relative to the earth is equal to the velocity of the fuel relative to the rocket plus the velocity of the rocket relative to the earth. We have found the fuel relative to the earth velocity, which is equal to minus v exhaust in this direction, and the rocket relative to the earth velocity is v. So we can obtain the fuel relative to the earth as v minus v exhaust. So we can obtain v minus v exhaust for the velocity of fuel relative to the earth. So when you substitute this to the fuel equation, we can see that the velocity of the fuel relative to the earth is v minus v exhaust. Now we can simplify the equation further. So m times v is equal to m times v plus m times delta v minus delta m times v minus delta m times delta v plus delta m times v minus delta m times v exhaust. So when we cancel the mv terms and also the delta m times v terms, we can simplify the equation down further, and we would obtain that m times delta v minus delta m times delta v minus delta m times v exhaust would be equal to 0. After simplification, we can obtain the equation here, and we know that this particular term delta m times delta v is very small. So we can neglect the particular term delta m times delta v. So the solution we obtain would be m times delta v is equal to delta m times v exhaust. As we can see, we can divide both the sides with the delta t terms. And we could obtain that this is the acceleration. We can see this is m times a is equal to delta m over delta t times v exhaust. We can also proceed that this delta m with the differential equations. So we know that at time simple t, the mass would be mt would be equal to m, whereas at time equals t plus delta t, mt plus dt would be equal to m minus dm. So when we apply the differential equation, we can see the dm term. So when we see what the difference of the m plus dt minus mt, it would be m minus dm minus m. So we will obtain that this is equal to minus dm. So we substitute that minus dm term to our equation we have obtained here. So we can see that minus dm over dt times the v exhaust is equal to the mass times acceleration. Here we have obtained the thrust with the particular situation of the rocket. This is termed to be the thrust. This is the velocity of the fuel relative to the rocket, and this is the rate of change of mass. So this is equal to the mass times the acceleration of the rocket. From the previous equations, we can see the m times delta v term is equal to v exhaust times delta m. We can simplify this with the differential equations and obtain m times dv is equal to minus v exhaust times dm. When we integrate these terms, you can see integration v initial to the v final dv would be equal to minus v exhaust times integration initial mass to the final mass times dm over the mass simple m. Now this is the v final minus v initial. This would be equal to minus v exhaust times ln m final over m initial. We can simplify this down further and see that the v exhaust times ln mi over mf is equal to the final velocity minus the initial velocity. This would be the change in velocity. So the change of velocity of the rocket in the direction we considered is equal to the exhaust times ln initial mass over the final mass. This is the change of velocity. These are the two scenarios associated with the rocket propulsion problems: the change of velocity and the thrust. This is it for today, guys. Thank you for listening.